Hi everybody, and welcome to a Working with Geospatial in Unreal Engine webinar today. I'm Sebastian Lozé, I'm the Simulation Industry Manager for Epic Games. I'm joined for this webinar by Alban Bergeret, our Simulation Solution Architect. Before we start, we need to ask us why are we here? What are we doing in this webinar today? Well, today in our webinar, we're trying to provide you with the best guidelines to go from your starting point to where you want to go. We realize that there's a lot of challenges surrounding the geospatial domain, and we want to illustrate a couple of tips, couple of tools that we are putting in place so that this process is becoming easier for you. There are four ways globally to create virtual environments. You can be extremely synthetic or using photogrammetry, real life data, or you can base your creation on the real world, as well as you can create environments that are totally imaginary. Now, on these four different approach, you're using different tools. The ones that we will be focusing on today are the ones related to GIS data, Geographic Information System data, as well as third-party processing tools that we will be describing in this little webinar. In a nutshell, when you're creating any virtual environment, you have a very unique solution. A very unique solution that is combined by all the criteria that makes your solution linked to your exact use case. And this is what we call our pipeline agility, allowing you to, no matter what is your challenge, finding the exact one solution that connects with your use cases. To do that, we're following the community and some key trendsetters, which are either from the entertainment or the simulation environment, as well as the architecture domain and the automotive industry. All these trendsetters, all these guidelines are provided by industry as well as community as well as policies. And it is this match that we're listening to make sure that when we take decision, when we define some pipelines, we match with the needs that you have and with the tools that you love. From 2019 to 2020, we've been pretty busy when it comes to geospatial environments. We loaded integration of tools like Triance 3D Graphics, the one that we will be talking about with Alban later on today, TerraVista, as well as specific formats like the E3 ArcGIS, the Cesium 3D Tile format, the OGC and the OGC CDB format, as well as the VBS Terrain server. We also integrated our first coordinate system plugin, allowing WGS coordinates to be handled directly within Unreal. All the efforts I mentioned today are just part of the beginning. There is a lot more to come, with photogrammetry and large open world at their heart. There will be one last thing, one more precision that I would like to give in the context of our work related to Unreal Engine 5, which will debut in 2021. The simulation community is very curious about our vision about large open worlds into Unreal Engine in continuation of our initial geospatial efforts. There is one point in particular which is interesting for those who are building large-scale simulation which needed confirmation. We are now able to confirm that Unreal Engine 5 will support 64-bit precision, aka double precision, enabling the developers to create large open worlds without precision issues. With that, I will conclude my little presentation by thanking you all for attending our webinar today, and I will leave the floor to Alban Bergeret. Alban, the floor is yours.
Hi everyone, and thank you, Seb, for this little introduction. My name is Alban Bergeret, and I'm Solution Architect for Simulation and Training at Epic Games. Today, we will talk about working with geospatial data in Unreal Engine. Before going further, I will just explain you the purpose of this webinar. We will start to speak a little bit of geographical theory about the geographic coordinate system. It will be a little bit boring, but you need to understand what's going on to deal with this particular issues. Then we will talk about accuracy system, accuracy problems or concern. We will talk about a GeoCoordinate plugin we made to solve some of these issues, and we will finish with a big hands-on part using a terrain modeler tool, which is 3D Builder from 3D Graphics. So what are geographic coordinate systems? In the real world, when we want to locate something, we use coordinates, and coordinates have a sense only when inside the reference system. And the reference system we use for locating something on Earth are the geographic coordinate system. To locate the Earth, we need to know the Earth, and we need to know its shape. We all know that the Earth is not flat. It would have been a very good idea because maths would have been so much easy, but actually not. It's a globe. And more than that, it's not a globe, it's not a sphere, it's a kind of potatoes, and if you want to be very accurate, maths are awful. We don't like complex math, so we will use an approximation of the Earth surface, which is an ellipsoid. Ellipsoid is like an ellipse, but rotating around the North Pole. It has an equatorial axis and a polar axis, two different lengths. And over time, while the measurements were more and more accurate, this eccentricity changed and different models were set up time after time. Currently, the most well-known one is WGS 84, with the figure you can see on the bottom right. This ellipsoid is known as a referent ellipsoid or a terrestrial reference system or a geodetic datum. And now we have different systems to give you a position on Earth. We can use a spherical coordinate system. We all know latitude, longitude, and elevation. We can use a projected system like MAPS coordinate with possibly elevation. And we can also use an Earth-centered, Earth-fixed Cartesian coordinates in 3D space. We will go deeper for this 3-1. The first one is geocoding, so it's a little bit out of scope for this webinar. So I will go very quickly over that. The first one is the spherical coordinate system with the latitude, longitude. And it's not really applicable for game engine because it's not a Cartesian system and the game engine are using Cartesian system. And for instance, I will take the example of Paris and give its coordinate in this different system. The other category of coordinate system are the projected coordinate system. We all know them because we have all played with paper maps when we were young at school, and it's a way to represent on a flat two-dimensional surface a part of a globe. It's a projection on a specific shape, and you can imagine a lot of different projections. And the drawback of this system is that there are some deformation around some specific location. Among these projected coordinate system, we have one which is very well used in the simulation field, which is a UTM projection system. UTM stands for Universe Transverse Mercator. The Earth is split in different zones, and depending on the location you are on Earth, you select a zone, and if you do that, you have pretty good accuracy around your meridian of interest. The coordinates are behaving very strangely, but it's just to avoid having negative values. And for instance, if I still take Paris into example, here are the coordinates of Paris in this system. This is a Cartesian system, so it can be used for the game in the game engine. Last one is the one we call ECEF for Earth-centered, Earth-fixed. It's a geocentric coordinate system. It's a Cartesian system, which origin is centered at the center of the Earth, and each axis is pointing in 3 directions related to the Earth. It's very interesting because there is no ellipsoid needed, reference the center, and this system is very often used when dealing with interoperability concern in simulation. And if I take the same example, Paris has coordinates like that in this system. Of course, it's good for game engine. So we have a lot of geographic coordinate systems, but how do we name them? There are different ways. Some simple and well-known projection systems have a small nickname like WGS84 or UTM. And we can also define precisely the coordinate system using a well-known text file, as you can see on the right. And we can also use an EPSG number. There is a website where you can find all these references. But it was, I would say, a little bit complex. I went very fast because we don't have plenty of time. But what is important to remember? Latitude, longitude are widely spread, but it's not good for game engine. We always need a reference ellipsoid, almost always. Projected coordinate system, it's good, but we have some deformation. And as soon as you want to go for round Earth simulation, it's not very well suited. And we have the geocentric coordinate. It works anywhere, but the maths are very complicated. And in that case, the gravity is not minus z axis, it's a force field. So it depends, your choice of coordinate system will depend on your use case. If you have a small scale environment, go projected. If you have a Earth-wide scale environment, go ECF. One last thing before going further. Did you notice the figure I used for coordinates? It's very huge number. It's 6 to 7 significant figures. And in fact, it's a nightmare for ourselves, the software developer. Let's see why. We have a problem on a computer. How can we store an infinite possible values with a finite amount of bits? We need to define an encoding convention, and we will have to drop some values. And this convention defines the way the floating point number are encoded as a bits on a computer. And this simulation website allows you to enter some actual numbers and to see that sometimes they get rounded, and you can get very high error sometimes. In that case, 25 centimeters. It's important, and much more if we go farther to these coordinates. It gives a lot of zit fighting, and you can do world queries for accurate positioning. So it's really an issue. How to solve that? What can I do? Well, I would say it depends. We have seen that if you use large coordinates, you will not like it because you will have accuracy issues. The better is to use small coordinates and so around the origin. But that it's in the UE4 context. In the UE4 context, coordinates are stored in 32 bits, so we have these issues. So we need to translate our data to keep it near to the origin and do the inverse maths as soon as we want to display actual coordinates. This is what we call world rebasing. The good news is that in the UE5 context, large coordinate with very high precision will be supported, and you will never have to care about it. It will just work. So right now we have to do rebasing. And in fact, there are two ways of rebasing, the static and dynamic. For static, you will stay on a small and projected area. You can keep just one fixed translation offset between your world and Unreal. Keep it for all the lifetime of your project. You import this translation when you import your data, and you do the opposite vector for every coordinate operation. It works very well for small database. But if you go further, if you want to display the globe like we did in Project Anywhere this year at ITSEC, you will need to rebase dynamically. Based on your actual position, you move all your geometry around your eyes to keep very good projection. The good news is UE4 already integrates this rebasing system, and you can just use it. It's very simple to set up in one pawn. So we have seen that we can use rebasing to have good accuracy, and we need to display coordinate from one system to the other. And when we are inside UE, we have no other choice than using these UE coordinates. But it's sometimes interesting to have information in spherical or geographic coordinate, or in projected UTM, or in geocentric, while keeping a good precision. And this plugin, the UE Geo Coordinate plugin, is a plugin dedicated to that. We use it in Project Anywhere, and the banner with the actual location of your eye is using that. This is an experimental version. It's currently available on GitHub. With currently a small feature set because it just handles the static rebasing origin, not the dynamic one. You can define geographic, projected geocentric coordinate system, and it will convert coordinate for you. Because of Project Anywhere, we added a lot of feature, and we will retrofit this feature in this plugin. And our ultimate goal is to make it part of the engine itself. So if you have feedback, feel free to communicate with us and give us ideas about what you would like to figure in this plugin. So what is included in this plugin? We have a world subsystem to make this conversion, but we also have a toolbar widget to display coordinate on screen, and a utility widget to query the coordinates from inside the editor when you are editing. It comes with the documentation. You can have a look at it to understand how it's working with a georeferencing subsystem. So now that we have done a lot of theory, we will start hands-on, and I will demonstrate you the general workflow for working with geospatial data in a projected use case. Earthwide use cases are more complicated. So the first step is gathering your geospatial data. You will need a digital elevation model, you will need aerial imagery, you will need vectors, sometimes taken for OpenStreetMap or other data sources. I invite you to first reproject them in your projected coordinate system, do some cleanup to have something very nice in input. Then we will use a 3D terrain modeler tool to import data, define our tiling for the world, define the origin for our static rebasing, and apply graphic template to each vector. Then it will generate terrain and export to Datasmith. In Datasmith, we will see that we will get one file which contains all the common assets shared among all tiles, and one specific file per tile. Tiling the database allows you to have the way to import very large terrain. You split your complexity in very small tile, or not that small, but in a lot of tile, and each time to import is easy to import, and you don't crash your engine by importing massive data. And then we switch to Unreal, and we use a tiled import mechanism to import this data in Unreal. We can apply a data prep recipe to optimize this dataset for real-time rendering. We can make some beautification step, and at the end we will see how to integrate the UE georeference plugin in our application. So thank you for your attention, and let's start the demo. Okay, so let's start with 3M3D. The first step in our workflow is to import data in our project. So I will go to my geospatial data folder and start to import the digital elevation model. The software asks me to save my project. Of course, I will do this, and I will call it folder. So the digital elevation model gets imports, and we see that it's not really straight aligned. It's because we didn't define a projection system. So we first go to generation and tell software that we want to use UTM, and for this specific location on Earth, we have to use zone 32. We apply, the workspace change, and now we have our dataset correctly aligned. Second step is to define our zone of interest. When we create this grid of tiles, we draw some tiles. Each tile will end up with some specific geometry. And by default, tile size is 5,000 meters. In our case, we have an imagery roughly with 50 centimeters per pixel. We want to go with texture around 4K, so the appropriate size will be 2,000 kilometers. So we define this tile size. Then we can draw again our area of interest. It's not that bad, and in order to simplify our job, we will round it to round number. So it's good, and now that we have done that, we can just focus to our area. Now that the working space is defined, we can start to import other kind of data, such as satellite imagery. So I come back to my imagery, open it, and we will just start by building this terrain to see how it would look like. When doing that, I have a warning. Okay, it's because I didn't define my origin. So I come back there, and in my settings for generation, I define my origin related to the grid in the lower left corner, apply, and to be sure I show position, and I get a message telling me that my origin will be there. Coordinates are expressed there, and it's very important to have these coordinates in mind because it will help us to define our static rebasing later on. So what I used to do is to create this single drawing. It helps me to remember all the coordinates of our interest zone. So here we go, and we will start again to build. It goes, and after a while, very quick while, we can switch to 3D view, zoom to extent, and we have our first terrain. It's not very nice because we used the default parameters, default settings for quality. So we will come back to the software and improve that. When we select the tiles, we can go to tiles, and we have an option there to define quality for each tile. You can define different qualities for different tiles, and it helps you to have a precise interest zone in the center and a lowest resolution zone around this area. So just to try it better, we will make something with higher quality and build again. This time it can probably take longer. But after a while, we will see our new terrain. During your work, you will always have to tune and test your generation algorithm. So it's good to work first with low quality settings, and then for your final production, raise your quality. And now if I go to 3D, I have something which is looking way better. But I see something which is annoying for my case, is the C is clamped at 0. And it's not what I want. So we can go back again into the elevation data, and for this specific case, we say that we want to go below 300 km deep. Okay, what I will do right now is to come back to my tile setting, and just for the sake of this webinar, I will lower the resolution to something very coarse to improve our computation times. Okay, so we have raster, we have elevation. Now it's time to import vector. We can run a wizard that will help us to import vector from OpenStreetMap automatically. So I already did it in the past, and so I start from scratch. I ask to download vector from OpenStreetMap, and when downloading, I will ask the software to create some attributes to this vector using a default table. I do that. The goal of this project is to associate generation algorithm to any kind of vectors. So we will see that right now. It's not easy to see the vector, so we will hide our DEM and imagery. And we have something very nice. So once again, it's quite complex because OpenStreetMap is very rich. And just to be more simple for this webinar, we will get rid of some data. So what I do there is to remove things that I don't care. So we will keep only the buildings, we will keep the roads, get rid of that, building though, and we will keep also the forest, and let's keep our card, and the other stuff we can get rid of it. In normal case, you will probably consider other kind of vector. Okay, so we have vector, so computation will probably take longer. So in that case, what we can do is just select a single tile and ask to build only this tile. We have a small warning message, and it goes, build again. And now we see the results. We automatically have roads and buildings. Of course, it's ugly because I took the default setting. I'm not a tech art, I'm an engineer. So I did it very quickly, and if someone with better skills than myself do it, it will look probably better. I thought the forest was slightly scarce, so I will change it to needle trees, because in this allocation we have needle trees, and I will make the trees farther. I ask to change the distance locally for this vector. My goal is not to teach you this software, it's just the basis. You can go with this software and the documentation, and you will be able to find something very easily. So it's time to build. So we can check last time for this tile to check if our density change is better. Okay, we have better trees, so let's go with that. Now, before making the final build, I will probably clean this vector there. So I select and remove them. Okay, we have something clean, we can go. Our goal is to produce for Unreal. by default, the Unreal exporter is not enabled. And to enable it, we have to go to the build settings and add another exporter, which is Unreal Datasmith. When you do that, it will produce Datasmith file, but you need to activate something very specific to Unreal to help the rendering. It's the instanced rendering. I'm not. Everything is explained in the documentation. I'll show you the documentation, and what I will do is very well explained in the documentation. So I need to ask that the needle trees that use the 3 needles will use instances. And when you do that, it will be exported to Unreal as instanced static mesh that batch trees together to have a very low draw call and a very good performance. I do that for any vector that comes with placed instances. So same for this guy. And okay, so we have selected the output for Unreal. We have all our trees. We could go to the settings and the tile grid raise the quality, but we will say let it like that to go faster. And it's time to make a final build, so I uncheck selected. I like to make a big reset to be sure that I don't have any remaining file, and then we can start. It will probably take longer, so I will make a pause. So back again, after a few seconds, everything has been generated, and now we can go in our 3D project file, and in Unreal Datasmith, we have our output. You will notice that we have two kinds of files. A common file, which are the shared assets, common to any tiles, and a dedicated UDatasmith file for each tile. And we will import all these files in Unreal using an importer utility widget. So let's go back to Unreal. I just created before a simple empty scene with nothing very important, except I imported the import tools provided by 3M3D. And these tools will help us to stream and not to stream, to import all these tiles. These tools comes with an import utility widget that first tell us be sure to have imported the 3D shared assets. So we go to Datasmith, we go back to our geospatial data. It's in 3D project, Datasmith terrain, and we load the assets file. Okay, import it at its default location, and that's all. In these shared assets, you will find all the texture which are in common, materials and geometries, shared geometries. And now it's time to import the tile. We need to fill the export folder and tells the project name. And because it's Datasmith file, you can data prep the assets. You can optimize them, compress them to have it better performance. And with the 3D import tools comes default data prep recipes that build and merge the buildings and the geometries. But you can define whatever recipe you want, and you will be able to apply it when importing. To tell the software we will import all the tiles, we have 5 tiles horizontally and 3 tiles vertically. So I go from 0 to 4, same for Y, and let's start import. This import will take a little time because the geometry will be processed, and so I will take another break and come back once it's done. Well, everything has been imported, so we can dismiss this window and see that we have our terrain with the assets. But if we look at the default assets, it's trees that have been provided by the software, which are not very nice. And what I did is I imported the trees from the Kite demo, which are nice trees, and I will use this tool to replace the trees I had in this file by other ones. So for that, there is just a data table with some maps that tells which is the old tree and which is a new tree. And so what you have to do is to go to the assets, find the geometries you want to replace, and say, okay, every time I have this tree, I want this one. Every time I have this tree, I want this one. Every time I want this one, and so on. You have understood. And you can also define the culling distance. It's important because depending on the size of your trees, you can select other clipping distance. And once you have defined your replacement table, you save it and you ask the software to replace the trees. And now automatically you have your 3D trees working instead of those. Okay, I will go on with this ugly database because I didn't make any polishing yet. I will show you a finished database later on, but now it's time to deal with the geospatial coordinate. In this project, in the Unreal project, I copied the simulation plugin, which is in fact the UE GeoCoordinate plugin that I took on GitHub from the previous presentation. And now this plugin is enabled and I can go, oh, sorry, I don't see it. I can go to the coordinate inspector utility widget and now it displays my coordinates under my mouse. I need to define my origin. Remember, I put it there. Why is it there? No. Anyway, let's go to project settings and tell this plugin that the origin will be, remember the figure before, will be at 268 and 472. I already, it's my default value. Okay. And now that I've done that, I can pick coordinates and see that coordinates are expressed in latitude and longitude, and also in the projected frame, which is UTM-32. And if I want to display it on the screen, I can just go to my level blueprint. I did it in the past. So on begin play, I will create a new widget. So what I do is create widget of which class, a class which is provided with a simulation plugin with is UMGGU status bar, and add to viewport. And that's all. Compile and play. And now I'm running my environment with actual geographic coordinate displayed. And here we go. Very quickly, I took geospatial data and I created an Unreal environment based on that data. Of course, I didn't make any artistical work. So now I will switch to another application, the same database, but polished and packaged as a final application. So in that case, what I did is I created an extended area to have the coast. When you are below, not far from the island, you see the other side. I tune a little bit the roofs and the facades. I change every trees and do other stuff like the arbor and stuff like that. I'm not very happy with the trees because it's just trees I took like that, and I think the billboards are not very nice. But if you just add a simple plane with a water shader, you end up in nice location. I hope you enjoy this presentation, and now we can go for question and answer.